All right, AP. This is a video that is called under your OneNote, Chapter 6, Labeling Periodic Table for Electron Configuration. Okay, so on your blank periodic table that I sent you, we're going to be labeling some stuff. If you don't see the symbols on your blank periodic table, I can't remember if I sent it with symbols or not. You may want to add some symbols. I would not waste my time with atomic numbers or mass numbers. That's not important for this, okay? This is a topic we did not get to do, and it's very, very tragic, but we're going to have to take it nice and slow. Because usually, like I said, in AP Chapter 6, I'm done in a week because it's a topic we did last year, and you guys do very well on it. So let's take it nice and slow. I'm also going to be including, we're going to be doing some sample problems, so I'm going to put a Word document under here. When you post these on OneNote, you're going to take a picture of your periodic table, all labeled, and then the practice problems that we also did. So you will see that on your OneNote, okay? Apologies, let me put it right here, Chapter 6, sorry. So see right here, Chapter 6, Labeling Periodic Table. You're going to take a picture of your blank periodic table that we labeled, and then you're going to include the pictures of the notes that we also did for this, okay? All right, let's do this. Let's go nice and slow, okay? So I'm going to use a highlighter. Use many different colors, highlighters, colored pencils, whatever you got, markers. So the first thing is we need to label where the orbitals for electrons occur, okay? So when we're doing electron configuration, it's about valence electrons, okay? So remember valence electrons versus core, okay? So valence electrons, these are the outermost electrons. And the outermost electrons, they're the most important electrons because they're the ones responsible for chemical bonding. So anytime you have ever written any formula for a cation and anion, it lost 2 electrons, it gained 3. It's these electrons that got lost or gained. The core electrons are the innermost, and I don't want to say the inside electrons because there's no electrons inside the nucleus. They're still surrounding the nucleus, but these are the innermost electrons. So these are the ones that are closest to the nucleus. Okay, and basically what their job is to protect the nucleus in case there's another atom coming around trying to take some protons or neutrons. That's called nuclear reactions. Okay, so we're not even going to go there. So on here, let's first talk about the 4 orbitals. Okay, so any electrons that come from these 2 groups, okay, they are primarily s orbitals. Okay, so remember there are 4 types of orbitals. Let's make sure we get that down too. 4 orbital shapes. Okay, so remember this is the quantum number for shapes. We have S, P, D, and F's. Okay, and that's all we're going to talk about. Another thing also on here is you're going to probably want to, in a black type of marker or something, you're going to want to put a thick line right there on purpose. Okay, really, 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 really thick. Okay. So we're going to label a couple things first before we start busting out the colors. All right, so we have quantum numbers. We have this little n, and that's called the principal quantum number, aka it also means the energy levels. Okay, also means the shells. Okay, all mean the same, but that is his true name, the principal quantum number. Okay, and then we have this guy, the 4 orbitals, that's the L number. Okay, we are not labeling the other 2 quantum numbers because they are not tested on the AP test. Okay, so from here to here. Now the principal quantum numbers, you can have anywhere between 1 to 7. And why 1 to 7? It's because the period numbers. So right here, this is n equals 1 and 2 and going all the way to 7. Now, before you start thinking, but Rodriguez, what about 8 and 9? They're down there. Remember, they're not there. And I already made a boo-boo. I skip 4 and went straight to 7. So 4, 5, 6, and 7. Okay. The reason why is because of this thick line right here. Those elements go right in that thick line. And thallium, or not thallium, thorium down here, right there. Okay, so that's where they go. So this right here, these are part of the N equals 6, and then the N equals 7. Okay, so if my stuff kind of gets moved around, it's because it's not liking me right on this document. Okay, so now that's the principal quantum number. Now where are the orbitals? Which electrons come from certain orbitals? Okay, so right here, I'm going to use my highlighter now. Now if you want to outline the boxes, that's fine. If you want to color in the boxes, whatever you want. These are called the s orbitals. Okay, so all of these, group 1 all the way to group 2, these are your s orbitals. Okay, so all of those. Okay, so any valence electrons come from here are s orbitals. So remember, that's what we're concerned about, are the valence electrons. Okay, the next ones are the p's. Now it takes a big jump all the way over here. Okay, and these are the p's. So I'm going to call this P1, and actually I could have labeled that right here, S1, S2. So I'm going to put it, notice I'm putting it as an exponent. There is a purpose, okay, and you know I'm going to get to it. So P2, P3, P4, P5, but then I'm going to draw a thick line right there, and right here, it's where it starts P6. I'm not including helium, okay, there's a reason why, and that's why I said there's a lot of stuff I need to catch up on. So all of that is the P. So I'm going to do that in a different color. Let's go yellow. So all of here, I'm going all the way down. Okay. All of that. Okay. All right. Cool. So those are the P's. Now I'm going to go back to helium, and I'm going to shade him orange because his valence electrons only come from the S's. He is what's called an S2. And when I actually do practice problem, I'm going to do helium so you actually see what he is. So they're the S's. So my S's are orange on the periodic table. My P's are the yellow ones. Okay. And then let's do the D's. Let's go blue. Okay. So I'm going to go blue. The D's are all right here. They're called the transition elements. So all of these are the D's. Okay, and I know, ladies and gentlemen, my periodic table is a little older version of the AP test, and yes, you may have stuff down here. It will not be tested on the AP test, okay? And if they ask you about, well, if so-and-so was placed right here under polonium, what would be its configuration? Okay, I've never seen them go past radon, number 86 on here. Never really seen them do like D's and F's, but we still got to cover it. So who knows what will happen? But I do know some cool stuff I don't need to go over because they don't test what's called the exceptions to the rule. So if you were taught what's called the exceptions to the rules, which are these two groups, that's great because it's going to be very important in college. Unfortunately, ladies and gentlemen, we are not going to discuss them because not tested on the AP test. Okay. So those two groups have some exceptions, but these are called the D blocks. Now, if you notice on the D blocks, how many are there? There should be 10. So we watched a video, and it should have been probably the 6.6 when we're talking about shapes. How many electrons can these guys hold? D6, D7, D8. I'm going to skip that one for a second because I need to fix it. These two exception ones, theirs looks like this instead. It's called S1D5, okay? And I'm just going to kind of cloud it because, like I said, it's not tested on AP test, but I just want you to have it labeled so when you do go to college and you take all your wonderful AP Chem, Honors Chem, CP Chem to college with you, and you have all these beautiful notes that people are going to be flocking to you because they're so amazing. And you'll probably be charging people because they're so amazing to see your beautiful stuff. Just remember Rodriguez did this for you, okay? So there's my D's. And then now I'm going to go over, let's pick Mr. Green. There you go. Here comes the F's. These are all the F's. Now I know they're inner transitions, ladies and gentlemen, but they don't have the same shape orbitals. So all of these are the F's, Okay, and that is my beautiful attempt of coloring. Okay. All right, so that's what they are. And if we were going to label them for time's sake, it goes all the way from F1, and it should go all the way to 14. And I'm going to let you label that, pause it, and go to 14. Okay. So with these, ladies and gentlemen, these are the 4 orbital shapes. We now know that there are G's and H's out there. Not tested. It's not going to go there. Okay, so these are the 4 shape orbitals we are going to discuss. Now, how to write an electron configuration. Okay, we need to make sure we mention a couple rules. Okay, for an s orbital, remember we talked about in a video how many electrons maximum they can hold. So this is called maximum. And all of these notes, ladies and gentlemen, if you want to put on paper instead, that's fine, because I'm going to eventually be erasing because I'm going to run out of room. But this is a lot of information. So usually when we get to this topic, I put on my notes, hey, bring your periodic table back from CP and honors because we've already done all this. We would have done it last year. So we didn't have to like do it again. But we're starting from fresh. So maximum number of electrons they can hold. An S can only hold 2. And why? Look how many groups I only colored. 2 groups. A P can only hold, look at how many groups, 1 through 6. They can hold 6 electrons. A D, how many groups did I color? All the way from 1 to 10. They can hold 10. And an F orbital, they can hold 14 electrons from 1 to 14. That is the maximum amount that they can hold. Once you get that limit, well, then you go to the next orbital. You fill it up. Okay? So we have a formula of how we write electron configuration. Okay? And I put an E with the little sign on it because electrons have a charge. So electron configuration, and it looks like this. Cool little formula. It's called N, the principal quantum number, the L, the orbital shape, and then an exponent. Okay? Now what that exponent is, that's the number of electrons. And it matters where you land. So basically, I teach it this way because if you're going to get a periodic table on the AP test, you might as well use it to your benefit for electron configuration. This is probably the awesomest way to do electron configuration, not because it's the way I do it. It's because it's the easiest and most simplest way, and everybody gets this. Okay? The reason why Mendeleev has this funky kind of shape to it, it's because of the electron configuration, because of the orbitals. Okay, it's not because he just took out a chunk of the periodic table and said, you know what, I'm not going to put anything right there in the middle. That's not the reason why. It's because of this topic. Okay, so I'm going to teach you a lot of things all at one time. You're going to see some of this from 6.6. 6.7 talked about how to fill up the orbitals. And then 6.8 and 9 at the end of the chapter is going to talk about how to do electron configuration. So I'm doing a little bit of 6.8 and 9 here because we need to practice. So I'm going to move this guy kind of like right here, and we're going to do some practice problems. Okay, so we're going to make kind of like a chart. So we're going to start with Mr. Hydrogen, and I'm going to go black marker. Okay, start with Mr. Hydrogen, and we are going to do its electron configuration. And I'm going to ask you several questions with this. Okay, no, we are not doing every element. I'm going to jump around, but then, and you'll see where I'm doing. Okay, so first the electron configuration. So remember, it has this formula: the principal quantum number, the shape of the orbital that the valence electron is in, and then the number of electrons that's in that orbital. Okay, so if I'm looking at Mr. Hydrogen, I see right there he has a principal quantum number of 1. So I'm going to put of 1. His valence electron is in the s orbital. So I put s. And these are all lowercase, ladies and gentlemen. Do not capitalize this. And look at what group he's in. He's in this very first group, and they have a 1. Ta-da! And that's what it is. Okay? That's how you write an electron configuration. That's how easy it is. But you know when Rodriguez says that's how easy it is, you know there's got to be a trick coming somewhere. Well, let's see if there is. So I'm going to ask you several questions. Okay? I want to know how many valence electron he has. Okay? So remember, valence electrons are the outermost electrons. That's the only electron he has sitting right there. So he's got 1 valence electrons. And then, before I keep going, I'm going to teach you a thing called orbital diagram. So you saw this probably in 6.7 video with the boxes. Okay, so orbital diagram, okay, is basically what we do is we draw a box. Never understood why it's a box since, you know, atoms are sphere shaped. Why not a circle? Okay, but, you know, I didn't come up with this. Orbital diagram is the arrows. And the arrows represent electrons. And we do the arrows up and down to representing the spin. So remember, there is a 4th quantum number called m(s), the magnetic. And with hydrogen, I'm going to do a lot of notes with hydrogen first. So the magnetic spin, and according to a scientist, Mr. Pauli said 2 things. Okay, he said that no atom has the same quantum numbers, and that an orbital can only hold 2 electrons. And then we talked about another scientist named Mr. Hund. Mr. Hund said in an orbital, you cannot have more than 2 electrons with the same spin. They have to have opposite spins. Well, if hydrogen only has 1 electron, well, then I just draw 1 arrow. You want to start it going up, then go up. You want to start going down, then go down. Whatever you want, okay? Whatever floats your boat, but just only put 1. Now, why only 1 box? Well, let's remember something from a video, okay? And let me go down. Whoops, let me go to Mr. Periodic Table. Okay, like I said, it's going to be a lot of notes. How many orbitals, the number of orbitals, can a S, P, D, and a F have? Well, you got to remember, what do those shapes look like? What did they look like? So if S orbital was called a sphere. Only one way you can draw a sphere, okay, aka Mr. Circle, and that's it. That's the only way you can draw it. So what does he have? He has 1 orbital. That's it. Oops, orbital. So aka 1 box, 1 orbital diagram. So a P, they were those dumbbells. Now to remember, how many different ways, X, Y, and Z, how many different ways can you draw those dumbbells? Well, if this is called P to the X, and then you could go P to the Y, and then P to the Z. I can draw a P orbital 3 different ways, so they have 3 different orbitals. But when you do a P orbital, you have 3 boxes connected, because this is called X, Y, and Z. Okay? And the D orbital, these were, I'm not even sure if I remember if I said the name of them, but they're called clovers. Okay? I'm thinking now that I'm not even sure if I even told you the name of those. So you may want to go back to your 6.6 video for the d orbitals. They are called clovers. Is because on a d orbital, it's kind of like the p, but got doubled. So like one of them looks like this, where it's like p to the y, and then you have the x, and that's just one drawing. How many different orientations did a D have? Well, they have 5 different orientations. So if they have 5 different orientations, well, then they can have 5 boxes. And you don't have to label X, Y, and Z, ladies and gentlemen. I'm just letting you know that's just how it is. And in these orbitals, that's the possibility of finding an electron, only in those orbitals. And an F, we don't need to know what his name is, okay? But don't even need to know how to draw them. But we do know, see the trend? See the trend? It's going to be number 7. So when we do F orbitals, there will be 7 boxes. Now the key to this, ladies and gentlemen, and I don't know why it always happens to some students, the boxes are connected. But when you go from an S to a P, there's this space between it. Or from a P to a D, there's a space. But if you are talking about a P orbital, you have to connect those boxes, or a D or an F orbital. Okay, so that is what it is. Now let me show you this cool trick. Remember what Mr. Pauli said? Mr. Pauli said, Mr. Scientist, it can only hold, the maximum hold of electrons is 2. That's it. So if an S orbital only has 1 orbital, well, how many electrons can I fit in that box? Well, 2. That's it. But a P has 3 different orbitals. and each orbital can hold a maximum of 2. Well, if each one can hold 2, 6. And a 5. Each one of them can hold 2. 5 times 2. Okay? Not rocket science. We're just multiplying. And then 7 times 2, 14. You remember what I just labeled on my periodic table? Ta-da! There they are right there. It's the groups, ladies and gentlemen. The periodic table, if you count how many P's and D's and F groups we colored, that's what it is. That's why this is so amazing with the periodic table instead. I've seen teachers and professors teach us in such bizarre ways. I'm like, oh my goodness, those poor students. I'm telling you, you're gonna like it this way, but you're missing a chunk of that information from last year. So I need to get you caught up to speed, okay? So that's what it is. So for Mr. Hydrogen that we drew, that's why, let me scoot him up a little, okay? That's why we drew the one box, because he's in the s orbital. That one valence electron is in the s orbital, okay? And then he has one valence electron. Now, I'm going to go to this, okay? How many electrons? I'm just trying to think of many different ways AP has asked questions. Unpaired electrons. How many are unpaired? Well, the key word is paired, okay? And I don't have a pair of electrons. So how many are unpaired? I have one electron that is unpaired, okay? So trust me, you'll see when we get to what a paired one looks like, okay? So kind of make a chart for all of these examples we're going to do. And if I add on to here, then I will, okay? So how many valence electrons? 1, and that's it. How many unpaired? 1. I am going to be adding another category coming soon called core. So if you want to sneak that guy in there, sorry, I just thought of it right now, okay? You can yell at me later. So let me get my little periodic table back situated, and let's get my example right there and put him up there to help us out. So now we're going to do Mr. Helium. So Mr. Helium, He. So what is his configuration? I always teach students, if you were going to teach somebody how to read a book, give them the directions on how to read a book, any book in the world. What do? Well, I always get that student that says, well, open the book. Well, yes, no duh, okay? But after you read open the book and you see the cover page and all the copyright information, table of contents, blah, 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 first chapter, first page, how do you read? Well, you start with the first line and you read left to right. And then as soon as you read that line, well, then you go to the next line and go left to right. And then you go to the next line and left to right. That's the rules for electron configuration, okay? So see Mr. Helium over here? You got to remember basic chemistry. That number right there, that's the atomic number. And what do we know about atomic number? Well, we know that equals the number of protons, and it also equals the number of electrons if the atom is neutral. Well, we're not even talking about ions yet. Not even going to go there. So if helium has 2 electrons, like hydrogen had 1, well, then what's my configuration going to look like? Well, first, what's the principal quantum number? It's a 1. N equals 1. And what orbital shape will he have? Well, he's going to have an S shape. So I got 1s. And how many valence electrons does he have? Well, he's only got 2 of them, and they both count. And that's it. So underneath, what would be his orbital diagram? Well, an s orbital, and now he's paired, okay? So how many valence electrons does he have? He's got 2. Those are the only electrons in the outer orbital. That's it. So he's got 2 electrons. And for core, for hydrogen, well, you don't have any on the inside near the nucleus because he's only got 1 valence electron. And same thing for helium. He's only got 2 valence. So now the question is, how many unpaired? Okay, so if you can see my heading right there, well, how many are unpaired? Well, look at that orbital diagram. Are any unpaired? Nope, they look pretty paired to me. So 0, okay? These are the basic questions that we always get for electron configuration, okay? I've seen them ask about sulfur, sodium, zinc. I think last year was zinc, okay? They can ask anything except the 2 groups that had those green arrows right there. They cannot ask you anything about anybody below chromium, and they can't ask you anything about anybody below copper. Okay, and like I said, it's because of some exceptions to the rules. So now let's get a little crazy. Let's go lithium. And oh boy, here we go. So Mr. Lithium, well, you got to remember something. Remember that number 3 right there. That means he's got 3 electrons. So when I do my configuration, I need to keep track of something. I need to keep track of total electrons. Because if my configuration doesn't show 3, something's wrong. Okay? So you're looking at Mr. Lithium, and he's now in the second principal quantum number. He's in the second one. So 2. And which orbital shape does he have? Well, his electrons have the S shape. Okay? And which group is he sitting in? Well, he's sitting in this very first group. So 2s1. All right? You're probably saying, wow, I get this. I'm getting it. Oh, here comes the big BUT. How many electrons did you just write? I see 1. Lithium's got 3. He's got 3 total electrons. Where's the other 2? Remember I told you, what's the rules for reading a book? You can't get to lithium's line to read it until you have filled every orbital up first. And that's a scientist called Mr. Aufbauer. You'll see his name in the 6.8, 6.9 video. In order to get to that orbital, I have to start here, like a book, and fill up this orbital first, 1s2. And then I go to this line, 2s1, and I stop right there. So this orbital from hydrogen and helium, it's still there. Because you could not have gone to lithium's configuration without having that orbital first. It always will start with 1s2. Okay? So this orbital diagram has that box. And then 2s1. What's an s orbital? It's a sphere. Only one box. And notice you are not putting them together because these are 2 separate orbitals. These are 2 separate orbitals. And because they are 2 separate orbitals, they have different energies. Okay? Talked about this in a video. Who would have more energy? That 2s would have greater energy than that 1s. Why? Because he's further away from the nucleus. Remember drawing those beautiful circles? Okay? That's your 1s2 orbital right there. And then now, 2s2. So the further away from the nucleus, the more energy he has. Okay? And what also do you notice the size of the atom? The size of the atom is bigger too. Okay? The more orbitals you have, okay, the bigger it is. Size of the atom, more orbitals, bigger atom. Okay? So, let's go back to the box. Okay? In the 2s1, how many electrons are in this one orbital right here? Well, I'm looking at it right there. There's my 1. So I only draw 1 arrow. Okay? Now, I'm going to give you the greatest trick on always to check your work. And if you check your work every time, I swear to anybody, you'll always get it right. Remember these numbers up here? They're called exponents. And what was the exponents representing? Well, you see our little formula for electron configurations, the number of electrons, the total number of electrons. Last time I checked, 2 plus 1 equals 3. Those exponents have to equal to the total electrons that that atom has that it's neutral, okay, the atomic number. So here's my question. How many valence electrons? You have to remember the definition of valence. And valence electrons, as you see up here, the outermost electron. Which orbital is the outer electron? Okay, and I'll even, sorry, I'm working on 2 different screens. I keep forgetting that. So right here, let's go with the highlighter. This orbital is my outer orbital. And how many electrons are there? 1. And as I get out of the highlighter, 1. That is my only valence electron. Well, then it's like, well, then what are these electrons then? That's the core, because those are the electrons that are closest to the nucleus. So that is your core electrons. So we're going to call that 2 core. And I apologize, can't see my headings no more. So now the question is, how many were unpaired? Well, how many are unpaired? That orbital's filled up. He's filled. But that orbital right there, he is unpaired. I have 1 unpaired. Okay? I know slowly, ladies and gentlemen, it's coming, but you just need more practice. And I know you're thinking to yourself, okay, Rodriguez, do a couple more. And you know I'm going to. It's not going to be a couple. You know it's going to be a lot. So, hint, hint. Let's go beryllium. I promise we're not doing all of them. I'm going to do a jump soon. Okay? Here's Mr. Beryllium right there, number 4. So I see Mr. Beryllium has atomic number of 4. So I'm just going to keep track of that. Atomic number of 4. 4 electrons. Okay? You got to start from the beginning, once upon a time. But I always teach students the very first time they're doing this, sometimes it helps if you write the ending part first and then go back and fill up the once upon a time. So right here, Mr. Beryllium, where is he sitting? Well, he's sitting in the second principal quantum number, so he's got a 2. Which orbital shape are his valence electrons? Those are the S. Notice I said which orbital shape his valence are in. And he's in the second group, called S2. Okay? Well, remember we said 4 electrons, but I still got to go back to the beginning of the story called Once Upon a Time. 1S2. It's filled up. And now we have 2S2. And we stopped right there. There it is. 2 plus 2. There's my 4. How many are valence? Well, remember which orbital is the outer orbital, this 2s. The higher the quantum number, remember 2 is bigger than 1. The higher the quantum number, that's the valence. So I have 2. How many are core? Well, those 2 from the 1s2, those are still the core. And how many are unpaired? Okay. Eventually, you're going to do this without the boxes. Only do it if you need to. Well, you got to remember, an S can only hold 2. And they're all filled up. And that's it. So how many are unpaired? 0. Okay. Now, I am going to go to boron, but then I'm going to do a little jump. Let's see what you got. Now, here comes Mr. Boron. Oh, we're going to get crazy. We're now in the yellow. Got to remember, he's got 5 electrons. Okay. So, let's write the ending of the story. Mr. Boron sitting right there. And look, he's in a p orbital, but his valence are in the p orbital. Okay? So what would be the end of his story? The end, they live happily ever after. Well, I'm in the second quantum, so 2. Now my valence have a p shape. And what group am I in on the periodic table? Well, I'm a P1, so P1. But where are the rest of the electrons? Well, still got to go. Whoever you wrote, like look at beryllium. There's literally the element right before it. This information just keeps getting written again. That's why I'm telling you, ladies and gentlemen, the beginning of the story will never change. It will always be once upon a time. It's where you ended. That's where it's going to change. And notice the 2 plus 2 plus 1 equals 5. So now it's going to get a little crazy. I'm going to ask you this question, valence, okay? How many valence? And I know you're thinking of a certain number called Mr. Uno, and it's not Uno, because here it is. Valence electrons. Actually, I want you to label it up here. Valence electrons are S's and p orbitals. Only are S's and p orbitals only. Well, maybe that now may change your mind. How many valence? How many valence electrons? You have to remember, valence are the outer orbital, the highest principal quantum number. And I got a quantum number of 2, and I got a quantum number of 2. These are the highest orbitals. They're both in the 2 orbital, okay? Now, just remember also, they do have different energies, very slightly different, but it is different. So remember when we said an S has less energy than a P, than a D, than an F? They do have slightly different energies, okay? But they are all in the 2 quantum orbital. There are 3 valence electrons. So now the question is, how many core? Well, if those are the valence, then whatever wasn't circled is the core. Ta-da, 3 plus 2 equals 5. Now, how do you draw the orbital diagram for S's and P's? Okay, I usually don't draw the boxes. I always tell my students, only draw the orbital diagrams for the valence, okay, or from the highest orbital, okay. Well, I don't need to draw the 1s2. I know he's filled, because you can't go to the 2s unless you have filled the principal quantum number of 1. So this 2s2, I know he's got a filled orbital, okay? Because I can't go to the P's until I fill the S's first. That is a huge, huge rule in electron configuration. And then a P, remember, has 3 boxes, 3 orbitals. I got 1 electron, and I'm going to fill it up right there with just 1. So if I have 3 valence, 2 core, well then how many are unpaired? I only got 1 electron in that 1 lonely orbital. 1. Do not call these unpaired because you don't even have an electron in there, okay? They're just called unfilled, okay? Be very careful with certain words. Just because one is unpaired and unfilled, they both have the same prefix, doesn't mean they're the same definition. These are just called unfilled orbitals. There's not even an electron in there, okay? So when we do orbital diagrams, we usually only just stick to the highest quantum number. So the 2s2, 2p1, okay? Now let's get crazy. Let's get nuts. I want to jump to nitrogen. And you're like, woohoo, okay, Rodriguez, calm down. Oh, there's a reason why. Nitrogen. I'm looking at him. He's got number 7. I'm looking. He's got 7 electrons, okay? 7, 7. Well, what's the end of his story? Okay, so I'm looking at principal quantum number 2 and principal quantum 2, and he's in the P shape. His valence are on the P, and he's in that 3rd group, so P3. However, I'm only staring at 3 electrons. Where's the rest of the story? Start at the beginning. 1s2. Over here, 2s2, got to fill them up. And now 2 plus 2 plus 3 is my 7, okay? How many valence? How many valence electrons? I hope you're not thinking 3. Don't think 3. Which ones are the highest orbitals? The highest orbitals are those right there. Don't have the same energy. The highest principal quantum number orbitals, okay? It's the 2s. So you got 5 valence. How many core? Still only that one. That's your core. And there's 2. Okay? Now, how many are unpaired? It helps to draw. Okay? It really, really does. So right here, it is my orbital diagram. He's filled up. And remember we said the P's had 3. Now here comes Mr. Hund. Hund's rule. Okay, which you hopefully would have seen, I think it's video 6.7 or 6.6. Hund rule said, I always like to call this the school bus rule. Let's say you're going to ride a bus, and according to Hund, an electron has to be in a seat first. You have to fill up the bus with 1 electron in each seat first before you can go and double up an electron in a seat. So if you were going to fill up, if you had your Mr. Bus right here, and you had your seats on this side and your seats on this side, he says, well, look, you got to put an electron in this seat and fill it up there and fill it up there. You got to put at least 1 in each one. And then, say you got more trying to get on the bus, okay, now you can double up. But you cannot double until you have filled 1 up in each seat first. And it always makes sense to students. It always connects them to that because it's like, okay, I see that. if I'm going to fill up a bus, I got to put at least an electron in each seat, and then I can go back and double up. Same for the orbitals. I got 3 electrons, and I can't just go and start doubling. I have to fill it up first with the same spin. I have to fill it up first with the same spin first. So then when I get number 4 coming in, he's going to then fill up that box, okay, with the opposite spin. So if I got 5 valence, 2 core, how many are unpaired? Well, I see 3 orbitals right here, and there are 3 unpaired electrons. Okay? All right, let's go Mr. Oxygen. And I know you're like, well, come on, Rodriguez, you said you're going to jump. Well, I just want to make sure. Okay? All right, so Mr. Oxygen, here we go. What's the ending of his story? I'm seeing 8 electrons. Just so you know, you could always write it right here, because remember, when you write a symbol, the number on top, the number on bottom, that guy right there, that's the atomic number, aka the electrons. Okay, so you can write it right there. I'm totally fine with it. So, oxygen's ending story, right there. Okay, so he's going to end with quantum number 2 and a P and then a 4. And before you say, wait, why not 8? Well, you don't have 8 here. This is the P4 group right there. So P4. So now what's the beginning of the story? Start in the beginning. Once upon a time, 1s2. And then right here, 2s2. And then I'm going to check. 2 plus 2 plus 4 equals my 8. Now how many are valence? I hope you're shouting it out. How many valence? 6. That's what I heard. 6 valence electrons. And my son's laughing. Thank you. And how many core? Okay, so here are my valence electrons. And this lonely electron that's closest to the nucleus protecting it, there's my core. Okay? Now, how many unpaired? Now, if you can see it without drawing the boxes, think of number. If you don't see it, then draw the boxes. I will not always ask for orbital diagram for every problem. That's why I want to see if you can see it first. Okay? But the boxes make it helpful. So I got 4 electrons, 3 boxes. So remember, Mr. Hund, we got to fill up 1 orbital at a time with the same spin. And then let's go back and double up. So how many are unpaired? Those 2 right there. They are unpaired. So there's 2. Okay? All right. I think we can get crazy. I think we can go to neon. Let's go Mr. Neon. So Mr. Neon right there has 10 electrons. He's got 10. So now what's his story? His story's going to end, the end. They live happily ever after. So he's the very last one in Principal Quantum 2. He's in the very last P. Okay, remember that line between it. He's in the very last P. And then he's got a 6. Okay? And that's it. Remember, the P orbital, that's all they can hold. See right there? P's can only hold 6. They're done. End of story. But what's the beginning? 1s2, 2s2. So those 3 numbers better equal to 10. Okay? So how many valence? Well, still from these ones, there's 8. And how many core? Still 2, because 8 plus 2 better equal 10. And how many unpaired? Well, unpaired, let's see if you can figure it out. If you can figure it out with drawing, great. Then don't draw it. But if I got 6, here comes Mr. Hund. 1, 2, 3, and then double up. 4, 5, 6. So how many are unpaired? 0. 0 are unpaired because every orbital is filled. Okay? That's the name of the game, ladies and gentlemen. I'm going to jump around a couple more. Swear, swear, swear. Let's jump around. Let me move my Mr. Periodic Table up. But I want you to add a note somewhere big, bold, on your periodic table and on your notes. I know it's in there in chapter 6.8. If S's and P's only are valence, well then what is the maximum amount of valence? Look right there. If S's and P's are valence, then what's the maximum amount you could ever have, ever? And it's 8. There is a very kind of voodoo number that the number 8 in AP, I'm sorry, not in AP, and just chemistry straight out, that number 8 pops up quite a bit. So this is about the first time you've probably seen it. But trust me, in my 25, blah, 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 something years, don't need to count those years, because then I feel gray and old. But the number 8 pops up a lot. So that right there is the most you can ever have. I always have students tell me this, and it just makes me cringe when I see this answer. Okay, and I know you better make sure you get this in 6.8. If S's and P's only count for valence electrons, only count, never, ever, ever D's or F's. Okay, so think of D's and F's, bad grades, bad orbitals. No, 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 don't want those. So the maximum I can have is 8 valence electrons. Okay, however, every element has valence. When I see the number 0 for valence, it just brings a gray hair, okay? Because I'm like, oh my goodness, there has to be somebody on the outside. There's always somebody on the outside. Not everybody's a core, okay? Every element has a valence. So before you put a 0 on a test or a quiz or AP test, please rethink it. Bold, highlight, whatever you got to do, ladies and gentlemen. Font 1000, okay? Every element has a valence, okay? They may not have a core like hydrogen and helium. They're only 2 elements that don't have a core, but everybody has a valence, okay? So that's why when we did hydrogen and helium, I didn't add that row yet, okay? It's because they don't have a core. But starting with lithium, they got core electrons, okay? So please, in your 6.8 notes, take some time. We're going to go to the third one, but let's jump big time, okay? Let's get crazy. Let's go, I think you're ready. Let's go aluminum. Okay, Mr. Aluminum right there. Let's see if you can handle it. Number aluminum, Mr. number 13, okay? Now pause it, see if you can do it, okay? Now that you've unpaused it, so where is the ending of the story? Well, Mr. Aluminum right here, he's in the 3rd quantum number. His valence electron's in the 3rd quantum. He's in this very first p orbital, which means P1. Well, he's supposed to have 13 electrons. Where's the other 12? Got to start from the beginning. Once upon a time, 1s2, 2s2, 2p6, 3s2. It's a book, ladies and gentlemen, line by line. 1s2, 2s2, 2p6, 3s2. It's the song that never changes, okay? And now add that up. 2 plus 2 plus 6 plus 2 plus 1. And no, hopefully without a calculator, that's 13. Okay? Here comes the magic questions. How many core? How many valence? How many unpaired? You got to ask yourself, what orbitals are the highest quantum orbitals? And it's any orbital that is the highest quantum number, number 3, and S's and P's only. There are 3 valence. That means everybody else is a core. So 10, because it has to equal 13. Okay? Now, how many unpaired? Now, I don't want to draw any boxes right now because I want to get to a d orbital and do some boxes there. But how many unpaired? Well, S2, he's filled. P only has 1. Okay, 1 unpaired. Easy peasy. Pretty simple. Let's go sulfur. Okay, sulfur right there, number 16. Okay, pause it, try it yourself. So the ending of sulfur, right there, he's still in the 3rd one. Okay, so 3p, and he's in the 4th box. 1, 2, 3, 4. He's in the 4th. Well, what's the beginning of the story? Same as aluminum's. 1s2, 2s2, 2p6, 3s2, 3p4. Okay? So 3p4. So how many valence? Only the quantum numbers from the highest orbitals, and those are the 3's, n equals 3's. Okay? And if that helps you to write that, n equals 3, there's 6. 6 valence. Remember, ladies and gentlemen, this has to equal 13. I'm sorry, it has to equal 6. Oops, we changed the element. Has to equal, blah, blah, blah. I don't even know what I'm saying anymore. There are 6 valence electrons, and it's got to equal 16 electrons. So 6 valence, 16. It's got to be 10. And look, 6 plus 2 plus 2 is 10. How many ampere? Well, look at it. If a P can hold 6, the maximum it can hold 6, and I got 4, how many are ampere? 2. Okay? If you need to draw the boxes, do it. But if you don't, then don't. Only do it when asked. Okay? Because it's a lot of time. I don't want to say wasted, but you know what I'm saying, wasted. Okay? All right. Let's go nuts. Let's go to the next one. Okay? Let's go Mr. Calcium. Before we transition to the blue guys, let's go calcium. So calcium number 20. Okay. Calcium at the end of the story, pause it, write it. 4s2. Okay. His valence electrons are in the 4s2. But what's the beginning of the story? Same as before. 1s2, 2s2, 2p6, and then right here, 3s2. And now we have to fill all these up before we can get over here to Mr. Calcium. Okay, I know you're getting the hang of this. And you're probably like, wow, this is fun, Rodrigo. This is cool. Why didn't we get to do this last year? Well, you know who we're blaming, Mr. COVID, okay? But we would have learned it. It's okay. As long as you got it now, easy peasy. How many valence? Think, which orbital is the highest quantum orbital? And it's only this guy right there, 4s2. So you have 2 valence. How many core? Total is 20. You got 2 valence. Not rocket science, 18. And how many unpaired? Well, how many electrons? Can an S only hold? 2. Yes, can only hold 2. So 0 unpaired. Okay? All right. It's getting a little bit crazy. If you need to pause, take a break, go to the bathroom, get a drink, definitely would suggest that. I'm going to set up some new paper because I'm almost out of room. I lied. I'm still good to go. So here we go. Let's keep rocking. There is no rule to what AP can not ask or ask when it comes to electron configuration, as in how far the periodic table it can go. It just only says there is no configurations for what's called the exceptions to the rules. So anybody in chromiums and coppers, okay, they cannot ask that. Okay, I'm going to show you what happens, okay, but it's not tested. Maybe I could throw it like as a bonus, hint, hint, okay. All right, here comes Mr. Scandium. And I know you're like, Rodriguez, come on, we can do it. But there's a trick, okay? And I'm going to have to find some room to write this. What's the ending of the story? Well, this is now called the D block, okay? So the D block. And if I take my eraser, I need to get myself some room. And I know you're like, what, Rodriguez, I don't have any more room. Okay, all right, well, maybe put it right here instead. With the D block, okay, what you have to do for the principal quantum number, the N number, okay, what you do is you take the principal quantum number minus 1, okay? And what I mean by this N equals 1, let me change that instead. Call it principal quantum number. Principal quantum number. You take the N minus 1, aka the period minus 1, okay? The period minus 1 is his quantum number. Everybody in the D block does this, okay? You have to take the period minus 1. So I know you're looking at Mr. Scandium saying, 4D1. No, no, no. That's what I'm saying. To find his quantum number, you have to take the period minus 1. So let me kind of make this come up some. Okay, so right there, everybody in the D, the period minus 1. Okay, so here comes Mr. Scandium. He is not 4D1. You take the period 4 minus 1. The ending of his story is a 3. He's the very first one in the D, and he's a 1. Well, what's the beginning of the story? Same as before. 1s2, 2s2, 2p6, 3s2, 3p6. And right there, I'm at Mr. Argon. Now here comes these two called 4s2. And you're like, whoa, Rodriguez, why is that 3D after the 4s? Okay, well, let's look at something called Mr. Notes. Hey, welcome back. 6.7 notes, see right here? We did this right here. See when it gets 4s2, 3D actually has more energy than a 4s. Now you're thinking, wait a minute, a 3D has a lower quantum number. Shouldn't he be right here? Well, that 3D can hold more electrons than that 4s does. So technically he actually has more energy than a 4s because he can hold more electrons. Whoops. He can hold more electrons than that 4s2. So he technically has more energy, so that's why we write him at the end. Okay? So once again, he has more energy. He can hold more electrons. That's just scribbling. Can hold more electrons than that 4s. And because of that, ladies and gentlemen, he actually is after 4s. Okay, so that right there, that's where the 3D is. And as you see, 5 boxes coming our way. Okay, so that's what I wanted to show you real quick. We saw it in the video, but it just probably didn't click then. So right here, valence electrons. Now, before you shout a number, think. The definition of valence electron is the highest orbital occupied, the highest quantum number. Which of these orbitals is the highest? Not the guy always written last. That guy is right there. A 4, a principal quantum number 4, will beat these two always. I know this guy has more energy, but that's not what I asked you. I asked you which orbital is the highest quantum orbital. And a 4s2 is the highest quantum number. It's an n equals 4, while these guys are an n equals 3. He's got more energy, but he's not the highest quantum orbital. So how many valence are 2? And remember, which orbitals only are valence? S's and P's only. I don't care if I wrote him last. Okay, he's not a valence electron. He will never be a valence. D's and F's are cores. Okay, so core electrons. So everybody else outside that box, they are all cores. So remember, Mr. Scandium had 21. I hope, ladies and gentlemen, you are not adding up all those exponents, because if 21 electrons, 2 of them are valence. Okay, come on, let's be like smart math here, smart math. And how many are unpaired? Well, remember, a d orbital has 5 orbitals and only 1 electron in it. It's right there. 1 unpaired. Every orbital has to be filled up first before you can get to that 3D. Now, you may see books, practice problems, anything like that, where they move this 3D like right there. You can. I don't, but you can, and it's not wrong. Okay, because some teachers and professors out there, they do teach it that way, where they put like all the 3s together, all the 4s together, all the 5s together. I don't. I like to keep it in order as the periodic table because it just makes sense to me. You do what makes sense to you. Okay, I am going to go to Mr. Vanadium real quick because I do want to teach you a couple of these exceptions just so you always have them with you when you do go to college. So I don't want you to think Rodriguez gypped you a education. So Mr. Vanadium, number 23, what's the ending of his story? Okay, so same thing as Scandium. I'm just going to change this last part to the quantum number minus 1, so 3. 3D3. Okay, oops, there should be a 3 right there. So 3D3. The beginning is the same. Okay, so I'm just going to go like this for time's sake, ladies and gentlemen. 4s2, 3D3. And no, don't you ever do that on a test, quiz, or AP test. It's never going to change this beginning. Okay, I'm just doing it for time's sake because I know this video is getting muy long. Okay, so how many valence? Still the highest quantum number, 2. If vanadium has 23, 2 of them are valence, then 21 must be core. And how many unpaired? Well, remember the boxes. 5 orbitals, 3 electrons in them. So how many are unpaired? There are 3. Okay? I don't mind if you draw the boxes as long as you understand it. Sorry, my boxes should have been the same sizes. But there's only 3, so 3 unpaired. How many unfilled? Those 2 right there are not even filled. Not even 1 electron's in it. Okay? I'm going to put Mr. Chromium. Okay, but I'm going to put a big star. So anybody in these rows, okay, these groups, cannot be asked on the AP test because they are what's called the exception to the rule. And I usually spend like a day on this in honors, and I'm sure in CP they do too, but you're going to get about a 2-minute explanation. What happens with these orbitals for chromium, it's not a D4. Because this is what happens. I know you're looking at 4s2, 3d4. It's about the energy, okay? There's usually a communication that happens with the orbitals and electrons, okay? And when these 2 are filled up, and this D has 4 in them, and D's looking like this, Mr. 4s, why do you have paired electrons and I just have this one empty orbital, one empty last orbital, and I want it to be filled so that way I have at least 1 in each one. And it doesn't do this with vanadium. That's why I did vanadium. It doesn't do it because he's like, look, I got to take 2 of your electrons to fill it up. I can't do that. But maybe I could take 1. What happens is there's a jump. There's a jump in electrons, aka excited electrons, hint, hint, okay, like flame test. What happens is one of these electrons, it'll jump to this orbital, and then, ta-da, this is what's called more stable with at least 1 electron in each orbital of those D's and the 3 D's. That is more stable for an atom to have at least 1 in each orbital than paired. So that 4s, it's like, okay, you can take 1. So what happens is you're left with 1, and this changes to a 5. That's why it's called S1D5. Everybody does it. Okay, take 1 from the S, give to the D. Take 1 from the S, give to the D. So the configuration is 4s1, 3d5. So now you were thinking, well, it has 2 valence. No, it doesn't. Now it has 1 valence. Okay. You're going to notice the D blocks. Okay. Well, let me pause there before I give you too much more info. The core, if Mr. Chromium has 24 electrons, 1 of them is valence, so then the core must be 23. And then now, here's the tricky part. How many are unpaired? And I know you're thinking, you know, number 5. Nope, 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 nope. They're all unpaired. But what about that guy? He had 1 taken. You have 6 unpaired. So be very careful. This is why I think AP takes this off, because there's a lot of craziness that's happening with these 2 groups. Okay? I don't think it's hard. It's just, like I said, it usually takes me a day. I go through this, and you got like a 2-minute Cliff Notes version. So that is what happens with chromium. So I think that could be a really good possible bonus question for anything like that. I like that. Hint, hint. Okay. Let's jump over to maybe Mr. Cobalt. Okay, we'll do cobalt and then copper, so that way you can see it also. Okay. So Mr. Cobalt, and he has 27 electrons, and same story from the beginning. Okay. So 1s2, 2s2, same from the beginning. I'm just going to keep going. And there is a shortcut version to this. For those of you who are like, well, why aren't you doing noble gas configuration? I'm not there yet. I'm not there yet. You got to get tortured the long way, okay? You guys didn't get to do this last year. I get to torture you. So right here, I'm just going to start right here, 4s2. Okay? And then I'm going to go to Mr. Cobalt right there. So he's principal quantum number -1. So 3D. And then 1, 2, 3, 4, 5, 6, 7. 7. Okay? So how many valence electrons? Okay, remember which orbital's the highest? He's still the highest. 27 electrons, 2 of them are valence. So then you have 25 core. Now how many unpaired? Okay, well remember a D can hold 10. They can hold 10 electrons. 5 orbitals times 2 is 10. So how many are unpaired? 3. Okay. Now I want to show you copper. Yes, he's one of the exceptions, but just want you to have it for those memories in the future, those star ones. Okay. Same thing. Takes one from the S, gives to the D. So originally he has 4s2, 3d9. And when you draw the orbitals for those 5, you're going to find out when you fill it up, he's going to have that one last orbital that's like, come on, 4s, come on, be a player, give me an electron. So it takes one and gives to the D, and it just fills it up right there. So this changes to a 1 and changes to a 10. It's not hard, ladies and gentlemen, but it's the theory that goes behind it. It's really important because this 3D is actually, it's more stable in a 3D10 configuration than a 3D9. It's always about energy. You want an atom to have stable configuration energy than unstable. So, like I said, it only happens with those groups. Everybody else, normal, okay? Now, I'm going to do zinc for a reason, because every time I teach students these exceptions, they think the exceptions continue to happen even right after it. No, ladies and gentlemen, the exceptions only happen if you land in those elements only. After that, everybody outside those 2 rectangular boxes, life is normal. It's back to normal. So Mr. Zinc, okay, Mr. Zinc right here. So everything's still there. And I'm going to just keep going. So right here I got 4s2. And now I'm all the way over here to Mr. Zinc. Okay, oops, I didn't mean to draw a star on him. He's not an exception, sorry. He's got 30 electrons. So I'm filling it up. I'm filling, bam. I didn't land in one of these elements with the exception. Then don't worry about it. So he's just normal filling it up, 3d10. And that's it. A D can only hold 10. Well, I erased it, sorry. A D can only hold 10. So we're done with the D block. And then when we go to the next element, now we're in the P. Okay? So 3d10. How many valence? Still got 2. Still got 2 electrons. And then how many core? Well, 30 minus 2. 28. And how many unpaired? Okay. He's all filled up. He's got his 2. D's can only hold 10. 5 boxes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Done. All unpaired. If you notice, ladies and gentlemen, every time you get to the end of that block, S2 filled up. The end of the D block, all filled up. End of the P block, all filled up. Okay, they're always filled up once you get to that last group, and then you go to the next block. So let's get a little crazy. Let's jump. I know it's going to sound crazy. 4 boxes. Ooh. Okay, I know. Calm down, Rodriguez. Calm down. So selenium. Okay, I'm probably getting a little crazy because I know this video is going long. So Mr. Selenium, right there, number 34. So 34 electrons. So beginning still the same. Still the same. 1s2, 2s2. Well, let's have fun. We haven't even written it in a while. 1s2, 2s2, and I already messed up. 3s2, 3p6. I'm at Mr. Argon now. Here comes potassium and calcium, 4s2. And now I'm going to go straight to the D block, but be careful. Quantum number -1, quantum number -1. But now we're back to normal. These are still right here. This is n equals 4. It goes back to normal. It's only the D block that does that. Okay, so now it's 4p, because now I'm in the P block. Here comes selenium. 4p, 1, 2, 3, 4. 4p4. Now you know I'm going to ask it, how many valence? How many valence electrons? Which orbitals, plural, are the highest quantum number? Well, you have 4s2, because it's n equals 4, and I also have this one. So that's why, ladies and gentlemen, you can't always think it's the last thing that you write. It has nothing to do with that. It's the highest quantum number. And 2 plus 4 is 6. Okay? What's the core? Well, 34 minus 6 valence, okay, you have 28. And how many are unpaired? Well, think about it, ladies and gentlemen, what's a p? Hint, without the arrows. A p has 3 orbitals, 4 electrons in it. How many unpaired? 2. Okay? Let's jump big, okay? Let's go Mr. 44. Ooh, we just jumped like 10 boxes there. Okay, 10 boxes, number 44. Before I have to get some new paper. 44, right there. Okay, so 44, I had to go through all of these. And right here is 4p6. And then 5s2. And I got to get all the way to that guy. Okay, name of the game never changes. 1s2, 2s2, 2p6, 3s2, 3p6. And I promise, ladies and gentlemen, you're going to get so fast at this, you don't even need the periodic table. It just keeps going and going. So right now, I'm at zinc, and then here comes gallium, 4p, filling up all the way to krypton, 6. And now we're at quantum number 5. So these two right here, 5s2. And I know you're thinking 5p, you're thinking 5d, 5d. No, quantum number -1, quantum number -1. 4d, because remember, this should have been a 5, but it's not. 1, 2, 3, 4, I can't even count. 4, 5, 6. And then a 6. I'm not landed in one of that exceptional boxes. Not there, not there. So how many valence? Okay. So how many valence? Well, which orbital is the highest quantum number? Ain't the last one. He's right there. There's n equals 5 right there. That's the highest orbital. How many valence do I have? I have 2 valence. How many core? 44 minus 2, 42. And how many are unpaired? Well, everything's filled up. That guy's filled up in S. But what about this D block? He ain't filled up. Remember, 5 boxes and only 6 of them in there? He's got 4 unpaired. Okay? I know you're getting the hang of this, but I do need to get to some F blocks too, and I know this video is going on to the end of time. So let me get a new piece of paper. Let's get rid of you. There you go. Okay? So let me bring him down some. Okay? And I'm going to go, let's do a big jump. Let's go Mr. Barium, okay, number 56, so I can get to this part right here. So Mr. Barium, barium right here is, what is he, number 56, okay, so 56. So I have to get through all of these guys, all of them, and get to here, okay. We can do it. We got it. Sing the song. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now here comes the quantum number of -1, 3d10. I'm at zinc. And now 4p6, okay, right there at krypton. And then now we're in the 5s. 5s2, quantum number -1, quantum -1, 4D10. I got to fill it all up. And then now back to the 5s. 5P6. And then here we go, last two. Quantum number 6S. 6S2. Okay. How many valence? I'm like, literally, this thing goes on till the end of time. I'm out of room. So how many valence electrons? Well, which orbital is the highest? No, I got 4s, I got 5s. Oh, look, there's number 6. 2 out of 56, 2 are valence. So core is 54. And how many are unpaired? Remember, ladies and gentlemen, all these orbitals have to be all filled. They all have to be filled because you can't get to the outside till you get all these filled, and they're all filled. How many unpaired? None. Everybody's all filled up. Okay? So this is when it gets a little tricky. I'm going to scoot this up some because we're going to do an F block. Okay? I can't even remember the last time I have seen an F block. I don't think I've ever seen anything past number 86. So I am not going to test you on anything past number 86. Okay? But here's the problem. See Mr. LA right here? LA right here, this is really 5. Let me write it in black. Quantum number -1, 5D1. But then we come down to the F's. Okay? So there's like 14 elements sitting right there in that block right there. And so we got to come down to the F block. So right here, Mr. LA, number 50, who is that, number 57? He's got all of this stuff, all of this. Then it goes 6S2, okay? For time's sake, ladies and gentlemen, that's the only reason why I did that. It has 6S2, and then now you got to go 5D1, okay? So how many valence? These still my valence. And now I have 50, what is that, 2 valence, so 55. And how many are unpaired? Just this 5D1, that's the only one unpaired I have. But now it gets crazy town. Mr. CE, literally the next box over, number 58. Same thing, still the beginning of time. But I got to go 6S2, and I got to hit that box first, okay? So 6S2, 5D1, and then I got to come straight down here, okay? Here we go, we got a new rule. Remember the transitions? Well, these guys are still transitions too, but they got a funky rule too. Anybody here, their principal quantum number is the period -2. -2. So I know you're saying, well, that should be a 6F1. It should be 6F. No, it's 4F1. The quantum number -2. Okay? This usually takes me a day to do this part, the D's and the F's and honors and CP. So you're getting the short, sweet version of it. Same thing right here, the quantum number 7, 7 -2. So these are really the 5 F's. Okay? So if you want to label on your periodic table, do it. Do it, do it. So right here, Mr. CE. So I got 6S2. I got to hit LA first. And then I come down here to C, and I got 4F1. These still are not valence electrons because valence are only S's and P's. So right there, that is my only orbital for valence. So I'm still going to have 2. If you haven't seen the trend, usually when you hit these blue and green boxes, it's either going to be valence 2, and only those special boxes have 1 valence. But you're going to have 2. Core, well, 2 minus 58, 56. Now, let me trick you. How many unpaired? I know you're thinking 1. He's unpaired, and that one's unpaired. So you have 2. Okay? So what happens once you get to the end of the story? Once you get all the way through here, then it's called Mr. 14. Okay? And I don't want to just jump little boxes because, like I said, I know this video is going on to the end of time. So Mr. LU, okay, he's still the beginning. He's still the same, 6S2, but you still got to hit that LA box, okay? And then right there, 5D1. And then right here, 4F14. Okay, because remember the F's can hold 14. How many valence? Still this guy. And usually on test or quiz, it's coming back to me. I usually have you circle the orbital that the valence are. So get kind of used to that. So we have 2 valence. How many core? You have 69 core. And how many are unpaired? Well, that guy's paired. I got all 14 paired up because remember the F block? They have 7 boxes. 1, 2, 3, 4, 5, 6. And you fill it all up. Da, 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 you fill it. That was really bad. I know, Rodriguez. It's all filled up. But how many are unpaired? That's the only orbital that's unpaired. So 1. So now that we go Mr. LU, you're like, whew, end of story. No, ladies and gentlemen, now you got to go back. Now you got to go number 72. So what does that look like? So here comes Mr. Hafnium, number 72. Okay, so same thing. Once upon a time, it's all the same. 6s2. I still got to hit Mr. LA. Got to hit that box. So 5d1. And then I came down here, filled him all up. 4f14. And now you're like, wait a minute. Okay, now I'm back to the D block. And before you write 5d2 and start celebrating, you have to remember basic chemistry. It's got to equal 72. If you add up all those exponents, it ain't 72. You have too much, okay? You don't rewrite the orbital. You don't rewrite it. You just go back and change the number. 5d2. You just go back and change the exponent. Do not rewrite it. Don't rewrite the same orbital twice, okay? Just go back and change a number. So how many valence? Still got my 2 valence. And I know my data table is all crazy. How many valence is 2? The core would be 70. And how many are unpaired? Well, that guy's filled. 4, 14. 14 is the highest number I can go for the F's. And the D, it's only got 2. So for unpaired, let me screw this up. For unpaired, I have 2. Okay? And then, ladies and gentlemen, you just keep filling it up. Just keep filling it, and then you go to here and fill it up. That is all I'm going to ask you up to 86. But if you had to keep going, well, then you go to AC, and then you jump down here. Okay? So last one. Let's do the last one, Mr. Radon. And I know you're like, thank goodness Rodriguez is done. Let's do the last one, Mr. Radon. So go from the beginning of the story. 1s2, 2s2, 2p, and I've already messed it up. I know, I haven't moved from the seat in a while either. 2p6, 3s2, 3p6, 4s2, 3d10, remember quantum number -1, 4p6, 5s2. So right now 5s2, we're looking about right there. And then quantum number -1, 5p6, okay, I'm just out of room, 6s2, so right here 6s2. Now, there's no point to go 5d1, 4f14, and then come back, okay? Just go ahead and you're going to fill it up anyways. It's all going to get filled up anyways because I got to go over here. So then 5d10, okay? If you want to write 5d1, and then go down here, 4f14, okay, so now you're right here. Then you go back here and fill it up. Okay, then change that 1 to a 10. That's how easy it is, okay? Trust me, the more you practice, the more you'll get this. 4f14, so now I'm right here, Mr. Mercury. So now what do I come back to? 6p6. Okay? Last questions. How many valence? And at this point, you're probably like, I don't care, Rodriguez, how many valence? So the highest orbitals are the quantum number 6. You got 6s2, and you got 6p6. So you have 8 valence electrons. You got core. How many core? Everybody else is a core. So 8 minus 86 is 78. And how many unpaired? Everybody is paired. They're all paired. Okay? That's configuration. That usually takes me a week in CP and honors. Sorry, I didn't mean to start deleting that on you. And you got the 1.5-hour version. Yes, it's been an 1.5 hours. So last thing I want to show you. Is there a cool trick to figuring out how many valence just by looking at the periodic table? Absolutely, there is a cool trick. Okay, remember the valence? Maybe let me highlight them in pink. The valence electrons are these pink ones. Remember, S's and P's, S's and P's only. Hey, count up how many groups I just colored. 1, 2, 3, 4, 5, 6, 7, 8. Remember I said, what's the maximum valence? Ta-da! If you know which element is in the group, then you know how many valence. Like if I said nitrogen, I don't even want the configuration. How many valence electrons does nitrogen have? 1, 2, 3, 4, 5. He's got 5. All you have to do is just count. How many does chlorine have? How many does chlorine? Count it up. 1, 2, 3, 4, 5, 6, 7. Bam. I don't even care if you go to the transitions. How many does tellurium have? Who cares? We don't even look at the D's and S for valence. 1, 2. Skip them. 3, 4, 5, 6. Okay? It's the coolest trick ever. Use the periodic table. He is your best friend. Use him to your advantage. But be very careful when I say this next question. Last one, I promise. How many does helium have? If you just look at the periodic table, how many does helium have? And I know you're looking at, he's got 8. Whoa, whoa, whoa. He's only got 2 total electrons. He's only got 2. He can't have 8. He in his dreams couldn't even have 8. The most valence helium has is 2. And if you look back to the beginning of all these notes you just did, he has 2. Okay, so be very careful when you do this last group. These guys have 8 valence electrons, but not helium. He's only got 2. Ladies and gentlemen, I'm proud of you if you've made it through this and you understood it. And if you didn't understand, I guarantee you will when we do homework this week. Have a great night. And I'm done.